Hey, it's Maya, and I'm here to tell you about the relatively unexplored world of base values, empty values, and the infamous null. But I'm getting ahead of myself. Let's talk about primitive types first, and I'll get to null and objects later. All primitive types have a version of themselves with a lack of a real value, but these values are not very well known. This is because when you only initialize a primitive variable, the compiler won't let you use it because the variable is classified as unassigned. The classification is a sort of label for the compiler to use, to make sure the variable isn't used with no value in it. There's an example of that right here, where I declared an int called uninitialized with no initial value. When you let the compiler process this, it says, of course, that the variable hasn't been initialized. So, since variables don't ever get a value from a declaration statement alone, the only way you can see the elusive base values of primitives is if they are fields in a class. Whenever an object is created of that class, the primitive fields will be automatically initialized to their base values. Here's a class I made to illustrate this named project class. In it, there is a variable of every primitive type. When an object of this class is created, all the variables are set to their base values, and then I print them all out on this line. For all the number types, int, double, long, short, float, and byte, the base value is some form of 0, depending on if the number uses decimals. With Boolean, the base value is false, which is a value specific to Boolean alone. And then there's char, which is the reason I used bars to separate these values, because the base char value looks like almost nothing. The char type is composed of many different characters, each with their own numerical value if you were to explicitly cast them to ints. A tool called the Unicode table demonstrates this. On it, you can see all the chars and what their numbers are. When char is a field in a class, it is automatically assigned to its 0 value as well. But this is not the empty space you would expect, although printing it does make it look like a space. In this code, you can see that I'm printing the visible and int value of the 0 char in the Unicode table and the space char. They look the same, but they have different numerical values. Though a space is of course an existent char, the base value for char is the 0th value in the Unicode table, which is a hidden box with the letters NUL in it. Actually, the first 32 values of the Unicode table are all boxes like this, and they all print out as spaces, or at least they look like them. But they are in fact helper characters that Java uses to deal with text. For example, the 10th char in the Unicode table is a box labeled LF, which creates a new line exactly like the whack and escape sequence, or a print line statement, because this is the char that makes those things happen. Here I wrote some code that prints out this char like the other ones, and the visible value of the char only shows because the 10 value is on the next line. The real space char, when cast to an int, is valued at 32 because there are 32 of the hidden boxes before it and Unicode is 0 indexed. Strings are a bit different, since strings are objects, not primitive types. Technically, there is such thing as a 0-like value specific to string, which is an empty string. However, an empty string is still an object, so it cannot be explicitly cast to an int. The empty string is just an empty set of quotes, and is remarkably useful in code to assign a string to this value. While chars have the disadvantage of only holding one value, a string can be added upon unaltered. This means that creating an empty string before a loop can let you easily create a string made of many other strings. Here I made a loop that does this, with an empty string that is modified by it. You can add a string to it many times to create a bigger string, in this case being 10 highs bunched together. This is all well and good, but what if string could have more than a fake 0 value? What if the string could be absolutely nothing? Then you would have something that is partly value and partly type, and it is known as null. Imagine for a second that you had an empty string. It could have been any value, and empty is a value too. A string with the null value in comparison would be like the ghost of a string. It would exist, but have no substance. Null isn't restricted to just string. Any object, no matter how simple or complex, can have a value that is null. Null is a bit like the 0 value of objects, because all objects use null just like all primitives use 0 for their base value. To make an object null, all you do is declare it without instantiating it at all, or just assign it to null right after the equal sign. Just like any other value, null can be printed. Here I made two values that are null, and they can be printed the same as the primitives were. Null is mainly useful because it acts as a marker, similar to unassigned primitive types. The compiler will refuse to work with null objects in most cases, which prevents you from using a value until you know it is set to the right amount, instead of setting them to random values until you get the real one. Doing that can cause mistakes. If you ever tried to use null, Java will throw a null pointer exception and crash, like right here where I tried to compare a null object and a runtime error occurred. Here's some interesting properties of null. It can be concatenated with strings and itself and printed. This is because the Java developers said that concatenations must always succeed, so since null is grammatically correct according to the compiler, it will compile and run without issues. Like in my code, you can concatenate null variables with strings themselves and null as a value by itself. Because null is used in all objects, you can test for a null value using equals equals, the only time when that's useful for object comparisons. These lines can tell me for certain that a variable is null if you want to avoid a null pointer. Look at that, it's null. Finally, int a equals integer null compiles. This works for any primitive, although the program has a null pointer runtime error if you try to actually run it. The compiler sees the int classification and it knows it needs an int or something that turns into one easily. Integer being an object can take a null value, but the compiler also thinks that an integer contains only a value that can become an int, so it works until you try to do it for real. As you can see, the compiler tends to be pretty wacky when it comes to dealing with null. This is because null is not a normal primitive type or object. It is the only member of the null type and is defined as the subtype to every other Java type in existence. Null is definitely in a category all to itself. So there you have it. That's the strangeness of null and all the other empty souls of the computer science world. If you enjoyed this video, be sure to like and subscribe and check out all the cool videos from WHS. See ya!